For this lesson, we're going to finish off our quite lengthy discussion about the different ways that lines and planes can intersect. And we're going to finish things off with the intersection of three different planes. Now, the first thing I want to say before I get started here is you can always treat this as the intersection of two planes, figure out your solution to that intersection of those two planes, and then intersect that solution with the third plane. It's a more drawn out process, but it's also a valid way to go. So if you find trying to get your head wrapped around the different options here when we have three planes, if you're having a hard time visualizing that or working through the algebra, you do have a fallback position. You do need to do your best to try to grasp this because you are expected to do it this way, but you do have a way to do it if push comes to shove, you have a fallback position. So the first thing we're going to take a look at are consistent systems, and that means we have some sort of solution. And you can see a summary of these, including some very nice illustrations in the textbook on pages 520 and 521. So the first case is a point of intersection. So that's when all three planes come together in a way such that there's a single point where they all touch each other. In order to get this situation, all the normal vectors have to be different, so that's something you're going to want to look at because we should always be taking a look at normals. And the three normal vectors do not form a plane. They're not collinear. Now that's a little more subtle, and I don't actually normally recommend that you would investigate that, but it is something to keep in mind, particularly when you're trying to remember the diagram, which I'm going to show you in a moment. Another case where all the normal vectors are different is a line of intersection. And in this case, as I said, I wouldn't expect you to check this, but I just put this down here for your information. In this case, the three normal vectors of the three different planes, they actually form, or they are coplanar. They lie in the same plane. And that's why we get a line versus a point of intersection. We can also get a line of intersection when we have two planes that are coincident. Essentially that means we now have two planes that are coincident making a single plane, and then the third plane intersects that pair of planes along a single line. This is actually like our previous lesson on intersections where we were intersecting two planes along a line. And then finally, certainly the least interesting case is a plane of intersection, a single plane of intersection, and that means that all three planes are the same. They're probably just in a different algebraic form. Some of these things are difficult to visualize. So for example, you can see I have here an illustration of the green plane, which is labeled as 1, the yellow plane, which is 2, and the blue plane, which is 3. They are oriented in such a way that their normal vectors are all different, and their normal vectors themselves do not form a plane. They are not coplanar. And as a result, there is a single point of intersection where these three planes meet. That is in contrast to another case where the normal vectors are all different. You can see that here. If I were to draw on the normal vectors, there's the first normal vector, there's the second normal vector, and there's the third normal vector. Those three normal vectors are obviously all different, but they actually form a plane themselves. Now, I've done this as if they're at 90-degree angles. That's not necessarily the case. But the idea here is that these normal vectors themselves all form a plane. And when that happens, then the intersection is infinite solutions along a line of intersection. Third, we have a slightly less interesting case because we have two planes that are actually coplanar, and then the third plane intersects that new single plane along a line. And then by far the least interesting case is when we have three planes that are coincident. So I've drawn this with a plane inside a plane inside a plane, but you need to remember all three of these planes actually stretch to infinity in all directions, unless there's some sort of strange restriction in effect. So those are consistent systems. Inconsistent systems is where we have no solution, and again, I'll refer you to the textbook for a summary of that. So the first case, which is probably the most interesting case, is when we have each of the planes intersecting each of the other planes, but it turns out that none of the solutions of those intersections are the same. So what we actually end up with are three distinct lines of intersection, but none of them are the same line. Then we can have two lines of intersection. So in that case, we have two planes are parallel but distinct, so that's no solution. If they're parallel but distinct, they can't intersect. But then those two parallel planes are kind of chopped by the third plane. And so they actually, each of those distinct planes intersects the third plane. We have three planes which are parallel but distinct, so it's like three layers, one on top of the other. I'm going to show you all of these on the next slide. And then we have two planes which are coincident, so that's like I showed you on the previous slide. So essentially that's like one plane. But the third plane is parallel to those other planes but distinct from them. So visually it just looks like two planes that are parallel but distinct. So here is that one that I thought was the most interesting case. We have three planes, and as you can see, each of these planes intersects one of the other planes. The blue and the green intersect along this line, the orange and the blue intersect along this line, and the green and the orange intersect along this line. But the problem here is that none of those three lines actually intersect with each other, so as a result, this is an inconsistent system. There is no solution. Here is the second one I mentioned, which where we have two planes that are parallel but distinct. That's the orange and the green. And then the blue slices across each of those two planes, resulting in the blue-orange intersection line and the blue-green intersection line. But again, those two lines are actually parallel to each other, and so no point or no line of intersection, no intersection at all. Then we have three planes that are parallel but distinct from each other, so they'll never touch. And then less interesting than that is if we were to merge two of these planes together and then have that third plane, that would also be parallel but distinct. So we're going to work through some exercises here, but rather than going through all the trouble of the solving of the system, and I'm going to be using matrix notation for solving these systems, but please understand, you can switch these back to XY notation, no problem. For example, this first system starts off as 2x minus y plus 3z equals 2, 4x minus 2y plus 6z equals 3, 6x minus 3y plus 9z equals 4, and that system turns into x minus 1/2 y plus 3/2 z equals 2/3, 0 equals 1, and 0 equals 0. Those are the results we get from these systems. So we're going to be focusing on the matrix interpretation of these things. Now, to do this, and the order that you do 1 and 2 is really entirely up to you, but you're going to want to take a look at the normals of the equations and of the planes, and you're going to also want to take a look at your solution options based on the normals and based upon the result you got when you work through the equations or the matrix. And then, if it's possible, you want to actually solve. You want to come up with the point or the line or the plane of intersection. So taking a look at what we have here, first of all, let's take a look at the idea of normals. So the normal to plane number 1 is equal to the vector 2, -1, 3. And as I've mentioned in previous lessons, if you want to compare normals and you don't want to write everything out in a very formal way, you can just start doing, for example, a simple division. So I notice that 4 divided by 2 is 2. -2 divided by -1 is also 2, and 6 divided by 3 is 2. So that means that the normal vector for 2 is actually 2 times the normal vector for 1. So now I know that plane 1 and plane 2 are parallel to each other. And going through the same process, comparing the 6 and the 2, -3 to -1, 9 to 3, I see that the third normal vector is actually 3 times n1. Now, it's not always going to be so convenient for you to be able to make this comparison, so you do have to make sure you write down enough information so that you're not relying on doing this in your head with no mistakes. I did it this way because it was pretty simple and straightforward. So I've got my three normals are parallel, which means that I've got some options for how my planes look. What are my solutions going to look like? Well, parallel, that excludes this one, excludes this one, excludes this one. Because the three normals are parallel, I could have this one, so I could have infinite solutions. Three normals being parallel, I could have three but distinct, or I could have two of the planes the same and then one plane being distinct. So now let's take a look at what kind of information we get from our system of equations. Is there anything here that makes us think one way or another? Well, when I take a look at this, 0 equals 0, that makes me think of infinite solutions. And then when I take a look at this one, 0 equals 1, that makes me think of no solution. And then up here, this is the equation of a plane. So first of all, the fact that I have no solution here, the fact that I have a mathematical contradiction, this one wins the day. This is the most important piece we have here. This system is inconsistent because it resulted in a mathematical inconsistency. So that's the most important piece. The next thing, rather than mark that with a, I'm going to mark that with a star. So that's the most important piece. But from an interpretation point of view, what else can we say? Well, we got one piece that said infinite solutions, and then we got another piece that was the equation of a plane. So my interpretation of this, how could I get infinite solutions and no solution? Well, the infinite solution part tells me that two of the planes are coincident, and then one plane is distinct. But we still have no solution overall. Now, let's take a look at our algebra here. Is there anything that would lead us to draw that particular conclusion? So if I take a look at my coefficients, then I might say, well, to go from equation 1 to equation 2, I multiplied by 2 by 2 by 2, but 2 times 2 is 4. So those planes are not, they're not coincident. If I go from equation 1 to equation 3, or plane 1 to plane 3, I multiplied by 3, I multiplied by 3, I multiplied by 3, and 2 times 3 is 6. Well, that doesn't work. What about going from plane 2 to plane 3? What do I multiply 4 by to get 6? And the answer to that is I'm going to multiply that by 3 over 2. And if I do that, multiply by 3 over 2, then I end up 3 over 2, 3 over 2, and then when I get to here, I get 3 over 2 is going to give me 3 times 3 is 9 divided by 2. Well, that's 4.5. So it looks like those planes are not collinear or are not coincident either. So even though I had an intuition about this, you still have to consider the situation. So my guess that the two planes are coincident, that was actually incorrect. So what we have are three distinct planes. So it's good to take a look at this, and it's good to form your analysis of it, but you still have to fall back to algebra. So in this case, I had to test my intuition by checking the constants in this case, the 2, 3, and 4, and I came up with a different conclusion. Now, of course, I loaded that. I knew where I wanted to go there. I already knew it was three distinct planes. I'd done this question before. But I want you to understand that you need to double check these things. Okay, now how about this one? again, we take a look at our results. So in this case, so first of all, we know that our results, we have to treat them with a grain of salt. But there are some results that actually kind of win the day. And in this case, I take a look at this last line, which is giving me a 0 equals 1. And so I already know there's no solution. If I take a look at my normals, in this case, I have equation 1 multiplied by 2. So it looks like normal 1 is equal to 2, negative 1, 3. And normal 2 is 2 times normal 1. But notice that going from 2 to 3 is not double. So that means that 1 and 2 are distinct. They're parallel but distinct. Now what about going from 2 to 3, or sorry, from 1 to 3? That's divide by 2. Oh no, divide by 2 doesn't work. So n3 is not equal to, or I shouldn't say equal to, n3 is not parallel to n1 or n2. So now we have two normals, we have two planes that are distinct from each other. So we have something like this, and then we have another plane underneath that's parallel, and then we have the third one that's not parallel to them. And so that one is going to, if I can draw it, it's going to chop through, resulting in a line of intersection. It's going to result in a line of intersection with each of those two planes, but those two lines of intersection are going to be different from each other. So no solution, and we got that, of course, from here as well, that there was no solution. So our geometric interpretation, so therefore we have two parallel but distinct planes and a third plane intersecting both. But it's still overall no solution. Okay, taking a look at our normals here. Normal 1 is equal to 2, negative 1, 3. And a quick look very quickly shows me none of these normals are collinear. So all normals are different. Now when all your normals are different, that actually severely limits your possibilities. When all your normals are different, just to go back and take a look at our diagrams, here's a case where all the normals are different. Here's a case where all the normals are different. And here is a case where all the normals are different. So we have two cases. We have a single point of intersection, a line of intersection, and then no solution because the three lines of intersection are all distinct from each other. So what do you think we have here? Once again, from here, I have a 0 equals 1. That means I have no solution. And just from that information, just those two things together, I know I have three planes intersecting at three different lines. And that is also no solution. And I think this is our last example. I take a look at my normals first of all, and again I can see they're distinct. So my normals are different. Or let's be more specific, let's say that all normals are different. I take a look here, and from here I have 0 equals 0, and that tells me infinite solutions. And since the normals are different, but I don't have a contradiction here, it can't be the one we just looked at. And so the only other choices when all the normals are different are one point of intersection or infinite, which is along a line. So this one must be along a line. And the diagram that goes along with that, and I'll never be able to do it justice, there's a plane. Let's switch colors actually. So there's one plane. And those two planes meet there. And there is a third plane. And they also meet. So the line of intersection is that line right there, where all those three planes meet. But we still have to solve this. Now I've already done the majority of the algebra here. So let's take this first line becomes x plus 7/5 y equals 16 over 5. And the second line becomes y plus, not plus, let's make that minus 1/5 z equals 22 over 5. And this is something I'm going to parameterize. Because I know that I'm going to get a line of intersection, so I'd like to get the parametric equations for the line. And so the way that I parameterize this is, well, I notice that y is present in both of them. So I can do anything that I want to here. I could let x or y or z be equal to t. It actually doesn't matter. So it's actually, let's see, pretty simple. No, it actually makes the most sense here. If I let y equal to t, t member of R, so t is my parameter. And then this first equation becomes x equals 16 over 5 minus, now that would be minus 7 over 5 y, but because we've changed that, that becomes minus 7 over 5 t. And this equation with the z, I'm actually going to leave the y on, actually I think I need to do that one in two steps. So over here, I'm going to write that as y minus 22 over 5 equals, and I take the z to the other side, that becomes 1/5 z, multiply through everything by 5 equals z, and now I can write over here z is equal to 5, but instead of y, I'm going to write it as a t minus 22. And so there we have our parametric equations for the line. Okay? So I haven't gone through every possible case. I believe there were 8 cases I showed you between the consistent and inconsistent systems, but I've gone through a number of very important ones and some of the ones that are a little trickier to come up with. And that's it for this lesson. And you can see there's not a lot there by way of questions, but some of these can be quite involved. You're going to have to do all of the solving to get to the point where you're able to interpret the solutions as well.